All right, let's talk a little bit about supervised learning. So this will be actually the main topic for today's lecture. And supervised learning is one of the most commonly studied machine learning formulations, particularly if you're looking at practical real-world applications in industry. So the overwhelming majority of machine learning that is used in industry is supervised learning. The formulation, as I said before, is that you're given a training set which consists of tuples of x's and y's, and your goal is to learn a function f theta of x that closely approximates the true y. And you could formulate this as either something as simple as a linear regression problem, all the way to something as complex as classifying objects and images. It encompasses all prediction and recognition models trained from ground truth data, and it's a multi-billion-dollar a year industry. So there are billions of dollars being made through the deployment of supervised learning systems labeled typically with ground truth data from humans. The basic principles of supervised learning are quite simple, and we'll learn about those principles today. But of course, there are many details to actually set up supervised learning methods that work effectively, and that will be covered in multiple subsequent lectures. Okay, so some examples of supervised learning problems. In the left column, I'm going to list what we're predicting, and on the right column, I'll list what we're predicting it from. So predicting the category of an object based on an image, that's a supervised learning problem. Think of a few more supervised learning problems. You could pause the video, or if you're watching this in class, you can type it into the chat. What are some potential examples of supervised learning problems that you might be interested in solving? In order to formulate one, you have to say what you're going to predict, and based on what you're going to predict that thing. Here are some more examples. You could predict a sentence in French based on a sentence in English. That is also a supervised learning problem. You get data of English sentences and French sentences. You could predict the presence of a disease based on an X-ray image. Now, of course, if the disease can actually be diagnosed using the X-ray image, you might get an effective system. If the disease cannot be diagnosed using an X-ray image, you can still train your model, but it might just not do very well. You could predict the text of a phrase based on audio utterance. That is a speech-to-text system, a speech recognition system. And in general, you can predict some quantity y based on some input x. So the point here is that there are many, many very different problems, from NLP to speech recognition to medicine, that can be framed as supervised learning problems. As long as you can formulate it as having an x and a y, where your job is to predict the y from the x, and you can obtain ground truth label training data, you can probably formulate it as a supervised learning problem. Okay, now prediction in general can be very difficult. Here is a handwritten digit. I'll tell you this is a digit between 0 and 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Which digit is it? Well, if you look at this digit, you might say, probably a 5. It's kind of a pretty sloppy 5. It could be a 3, I guess. This digit, probably a 9. It could be something else. Probably a 3. Which one is this? Take a moment to think about that. What digit is that? You might think it's a 4. You might think it's a 9. If you're being really clever, you might say, well, I don't know what digit it is. It could be a 4 or a 9. You know, if I wrote my phone number on a piece of paper for you, and you wanted to call me, and I had written this digit, you might first type in the phone number with a 4 in it, and see if I answer. And if not, you might type it in with a 9 and see if I answer that, right? So in reality, if you were to actually see this digit, what you actually do with it might be informed by your uncertainty. And here's another example. A 0 could be like a backward 6 or something, or maybe an 8. It's pretty difficult to get the right answer if you're forced to commit to a single label. What if we instead imagine predicting probabilities over labels? So if we're looking at this 5-ish looking thing, We say, well, 0% that it's a 0, like it's definitely not a 0, it's not a 1, it's not a 2, well, it could be a 3, or maybe it's 0% 3, I don't know. Definitely could be a 5, maybe 90%, maybe we're pretty sure that it's a 5. And maybe like a small chance that it's a really sloppy 6, and maybe like a 2% chance that it's a really weird 8, right? Okay, so maybe that one is like a more clear-cut case. This next one, it could be a really ugly 0, like maybe someone's pen just slipped and they put a squiggle, so maybe a 4% chance that it's a 0. Definitely not a 1, definitely not a 2, definitely not a 3. It could be a 4, it could be like a really ugly 4. It could be a 6, maybe, just a really ugly one, like with a really big lower loop. And could be a really awkward 8, but probably a 9, right? So most likely it's a 9, but it could be some of these other things. The next one could be an ugly 0, could be a 3, could be a 5, it kind of looks like a 5, it could be a 6, with just a missing loop on the left side. So if we're allowed to output probabilities, we can much better express what we think is really going on. We might capture the fact that this 4 could be a 4, and it has a pretty high chance of also being a 9, and we're just not sure, right? So outputting probabilities gives us a lot more flexibility to actually express what we think is really going on in the image, and that uncertainty might be useful for actually making decisions later down the line. All right, so predicting probabilities often makes more sense than predicting discrete labels. And we'll see later that it's also actually easier to learn if we predict probabilities rather than discrete labels because of smoothness. Intuitively, we can't change a discrete label a tiny bit. Like we can't modify our theta values and see if the label becomes a little bit more correct. It's kind of all or nothing. Like if you're forced to output dog or cat, if you change your theta a little bit, the label probably won't change, and then you change it a lot and it might flip, but that large change might be hard to find. But we can change probabilities a tiny bit, which makes the problem of finding the optimal thetas easier because you can change them a tiny amount and see if the probabilities change in a direction that is closer to what you want. Okay, so given a training set, instead of learning a function that maps x to y, now we're going to learn a function that maps x to a distribution over y. And I'm going to denote this as p subscript theta of y given x. So it's actually a probability distribution over y conditional on x. It's a conditional distribution. So now we're going to be taking our input, maybe our picture of a dog, and outputting a distribution over its corresponding label y. All right, let's go through a little refresher on conditional probabilities. So we have two random variables. We have the random variable x, which represents the input. That could be the image, for example. Why is x a random variable? Well, x is a random variable because we don't know what x we're going to get. So there's some true underlying process in the world that gives rise to different x's, and we might get different ones. Y is a random variable that represents the output. And we could write the joint probability of x and y. Now, we know from our introduction to probability course that p of x comma y can be decomposed using the chain rule of probability as p of x times p of y given x. Right? This just follows from the chain rule of probability. You could also rewrite this equation by dividing both sides by p of x to get the definition of conditional probability. P of y given x is just p of x comma y divided by p of x. Okay. So if you actually know p of x and p of x comma y, you could recover your conditional probability, and in fact there are methods that do this. But in today's lecture we're going to take a different approach. We're going to talk about methods that learn p of y given x directly. I'll revisit this distinction a little bit later, but just so that you know the terminology, methods that learn p of y given x directly are referred to as discriminative learning methods. They're referred to as discriminative because their goal is only to discriminate between different y's. Methods that learn p of x comma y are called generative methods. They're called generative because such methods could in principle generate x's. But if you can learn p of x comma y, you can recover p of y given x from the definition of conditional probability. If this distinction doesn't entirely make sense to you, don't worry about it for now. We'll talk about it in much more detail later. But in today's lecture, we'll focus on learning p of y given x. Okay, so the first question we're going to ask is, how do we represent p of y given x? Remember, in machine learning, we just have a computer program that maps inputs to outputs. Except instead of outputting object labels, now we're outputting object probabilities. So instead of outputting one categorical label, we're going to output a bunch of numbers corresponding to the probabilities of every possible label. And the first thing we have to choose is how we represent this computer program. What is that computer program, and what are the parameters in that program that we're going to learn? So we're going to take some picture and we're going to output this table of numbers representing the probability of every class. So if we have 10 possible labels, our program needs to output 10 numbers. And these numbers have to be positive, and they have to sum up to 1 in order to be valid probabilities. So we can't just choose any computer program that just outputs 10 numbers. We have to somehow get them to be positive and to sum to 1. So that's the first challenge that we're going to deal with. All right, so before I had this example of a very rudimentary program. If x is below some line, and this below line function needs to be implemented, then output one class, otherwise output a different class. But we need to output probabilities. So how about this? We're going to say that p of y equals dog given x is x transpose theta dog. Okay, you don't actually want to take the pixels in an image and have a linear function on them, but let's just not worry about that for now. Let's say that that's a very low dimensional dog, right? Okay, that seems like a sensible choice. You're going to get a number. And then p of y equals cat given x is x transpose theta cat, right? So this defines a valid program. The program takes in x and it outputs two numbers, one for p of y equals dog and one for p of y equals cat. And it has parameters defined by the concatenation of theta dog and theta cat. Does this output a valid probability distribution? Take a moment to think about that. So a valid probability distribution consists of positive numbers that sum up to 1. The trouble with this program is that in general, p of y equals dog plus p of y equals cat will not sum to 1 unless the thetas are chosen very, very carefully. Right? So we're violating this constraint that the numbers are positive and sum to 1. So that's our first problem. Okay, so how about we change things a little bit? Instead of having x transpose theta dog be equal to f dog, or be equal to p of dog, we're going to have it be equal to some function f dog. So we have some intermediate function inside of our program, a subroutine, if you will, called f dog. And f dog just outputs x transpose theta dog. Just like we have this below the line function, we have an f dog function. And then the probability, the p of y given x, will be given by some other function that I'm going to call the softmax. And this other function is going to take in f dog and f cat, and it's going to force those numbers to all be positive and to sum to 1. So this is also a valid program. It's just a program formed by composing softmax with f dog and f cat. So you take your input, you run it through f dog, you run it through f cat, and then you take those outputs and you run them through softmax, and that gives you your p of y given x. And f dog and f cat are defined here as these linear functions. I haven't defined softmax yet, but the job of softmax will be to take these real valued numbers that f dog and f cat produces and somehow force them to be positive and to sum to 1. And if we can do that, then we have a valid program for producing object probabilities, a valid function with parameters that we can learn. Okay. Now, in principle, the softmax what I'm calling softmax here could really be any function. It would be nice if it's a one-to-one and onto function, but it could be any function that takes these inputs and outputs probabilities that are positive and sum to 1. Now, the reason I said one-to-one and onto is because you probably don't want a function that like takes f dog and f cat and throws them in the garbage and then outputs 1 comma 0 or something. Like 1 comma 0 sums to 1 and both of those are positive, but it kind of ignores the output of your learned functions. So you don't just want any function, you want to actually use the thing that you're putting in. A one-to-one and onto function would do this. If you're not sure, if you don't remember kind of your real analysis and one-to-one and onto don't make sense to you, don't worry about this. I'll explain it shortly. Okay, but maybe a more basic question is, why is it that pretty much any function could work? Like, don't we want something really special? Don't we want the right probabilities? Why is it that we can use any function that makes them positive and sum to 1? Take a moment to think about this. You could also write down your answer. That might help you to make this concrete. Why could this be any function? Why isn't it critical for this to be a very special function? See, your choice of function in machine learning is not meant necessarily to produce the right answer. You produce the right answer by choosing the right parameters. The function just needs to be general enough so that there exists a choice of theta that represents the right answer. So as long as this function doesn't lose too much information, you could probably choose theta dog and theta cat so that it outputs the right answer. You don't have to be that careful with that choice because you're going to be choosing the theta to maximize the correctness of your answers. All right. So, but let's talk about a particular function that we could actually use, right? So the point I was making on the previous slide, it doesn't matter all that much. There are many choices, but let's talk about a particularly good choice that we'll want to use in practice. So we have to do two things. We have to make them positive and we have to make them sum to 1. Now, given some number z, how can you make that number positive? There are a variety of things you could do, right? You could say, well, z squared is always positive, no matter what z is. The absolute value of z, that's always positive. You could take the max between 0 and z. That's also positive. You could also exponentiate z. That's also positive. These are all valid ways to make a number positive, and they could actually all work. The exponential function is especially convenient because it's one-to-one and onto. What that basically means is that it maps the entire real number line to the entire positive part of the real number line, which means that, in a sense, it's the least restrictive way to turn any number into any positive number, because every real number will map to a unique positive number, and there exists a real valued number that would produce any desired positive number if passed through the exponential function. The exponential function is not the only function that has this property, of course, but the fact that it's one-to-one and onto makes it quite convenient. So one-to-one just means the mapping from inputs to outputs is unique, so no two inputs map to the same output, and onto means that it maps to the entire range, in this case the entire range of positive numbers. So it maps the entire real number line to the entire set of positive reals. You don't need this property, it's just kind of convenient because then you're not like wasting a huge chunk of your number line. So don't overthink it. Any one of these would work. They have different trade-offs, but it's not that critical. But the exponential one is especially convenient, and since they're all okay, the exponential one is the one we're going to use. Okay, next thing is we need the numbers to sum to 1. So if we make all of our numbers positive by exponentiating them, how do we make them then sum to 1? Well, if you're given two numbers, z1 and z2, you can get them to sum to 1 by changing them to be z1 over z1 plus z2, and then z2 over z1 plus z2. This is called normalization. So normalization means you take each of the numbers and you divide them by their sum. And if you do this, then the resulting new numbers will have to sum to 1. In general, if you're given n numbers, then you take z1 and you divide it by the sum from I equals 1 to n of zi. So this is referred to as normalization. So armed with these two observations, we can now define the softmax function. The softmax function takes all of its inputs and it exponentiates them, and then it divides by their sum. Now, for the dog-cat example, it's a function of two inputs and it produces two outputs. So what I have written here is the first output, the dog output, right? So there's a dog input and a cat input, and a dog output and a cat output. So the dog output is the exponential of f dog divided by the exponential of f dog plus the exponential of f cat. What is softmax cat of f dog f cat? Well, that's just going to be the exponential of f cat divided by the exponential of f dog plus the exponential of f cat. So the exponential makes it positive, and the division makes it sum to 1. There is nothing magical about this. It's not the only way to do it. There are other ways to get numbers to be positive and so on. As long as you just get the numbers to be positive and to sum to 1, that's all you really need to be able to output probabilities. But the softmax is one particularly common choice. In general, you might have n labels, so not just cat and dog, but some number of labels, like 10 labels for these digits. And p of y given x is a vector with n elements, one element for every possible label. You have some function f theta of x, which is a vector-valued function with n outputs. And those outputs might not be positive, they might not sum to 1. So the softmax gives you the ith label, so p of y equals I given x, is the ith entry in the softmax function. So the softmax function takes in a vector and outputs a vector. And the ith entry of that outputted vector is the exponential of the ith output of f of x divided by the sum over all the dimensions of the output of f of x exponentiated. Right? So this is the softmax function. And its sole job is to make the numbers positive and to make them sum to 1. All right, so here are a few illustrations of the softmax in action. Let's say that you have two classes, red and blue. The theta values that are learned, they basically define a line through the space. And anything above this line has a larger probability of being red, and anything below this line has a larger probability of being blue. Right? So that's the effect that you're going to get if you do a softmax with these linear f's. And the line itself is actually the point where the probabilities are equal. So as the inner product between the theta corresponding to a particular label and x gets bigger, the probability of that label gets bigger. And if that inner product is equal to the inner product for another label, then the probabilities are 50-50. This is perhaps easier to see in the 1D case, because in the 1D case, I can actually plot the softmax, the output of the softmax on the y-axis. So here you're again classifying between red and blue, but they're one-dimensional points. So over here on the right, clearly the right answer is red. Over here on the left, clearly the right answer is blue. And in the middle, maybe you're kind of not sure. So intuitively, if you were to imagine a plot of the probability of red overlaid on this, think about what that plot would look like. Right? You'd expect it to be low in the blue region, high in the red region, and kind of close to 50-50 in that not sure region in the middle. So this is the decision boundary. This is basically the point where you cross the 50-50 threshold, and the softmax would look like this. So this is, the softmax, remember, it outputs two numbers, two probabilities, and I'm plotting one of them. I'm plotting the p of red. There's also a p of blue, but because there's only two classes, p of blue is 1 minus p of red. So that's why I'm only plotting p of red. And you can see that it crosses 50-50 right there at the decision boundary. It saturates to 1 on the right, and it saturates to 0 on the left. So it's almost 0 in the blue region, almost 1 in the red region, and kind of in between. So this is the softmax equation again for two classes, red and blue. The probability of red increases exponentially as we move away from the boundary, and then the normalizer keeps things summing up to 1. Now, as a brief aside, Why do we call this the soft max? Well, let's think for a minute what would happen if we were to take our thetas and we were to multiply them by some big number. So maybe this is our original decision boundary for a particular choice of theta red and theta blue. And now we will multiply them all by 5. If we multiply them all by 5, we get the same shape of the curve, but it increases much more rapidly to the right and it decreases much more rapidly to the left. It crosses the 50-50 boundary in the same exact place. It's just getting sharper. It's getting steeper. And if we multiply by 100, then the resulting softmax will actually look almost like a step function. Essentially, because the exponential function increases so rapidly as its input increases, then for any place where the dot product with blue is larger than the dot product with red, the exponential will force that to go almost to 0. And any place where the dot product with red is larger, it'll force it to go almost to 1. And there will be a very sharp change in the middle. Interestingly, this is very much like a max, right? You're just assigning a high probability to the label with the largest dot product, with the largest theta transpose x. So that's why it's called a softmax. It behaves like a max if the numbers going into it are very large, but as those numbers get smaller, it becomes softer. It has a gentler slope in the space of probabilities. But for very large values of theta, it looks very much like a max over the labels of theta y transpose x.